All right, so from the flashlight lab, we learned that when light comes in directly overhead, so like this would be like the surface of the earth. If I'm standing here with my 2 feet, I'd have to look up to see the sun. So all of the light reaches an area like this big, right? If we're just taking this amount of light, it reaches an area this big. But if we were to turn this and put it at an angle, kind of like how the Earth's surface is angled, right? So like if we were going to be setting this up, this would represent the equator, while something like this at this angle would represent like north of the equator, something more like New York, right? So the light gets more spread out. It's less intense, right? So intensity of insolation has to do with the angle. When the sun is right above your head, it's super, super hot, right? But when the sun begins to set and goes lower in the sky, it's less intense, so it's at a lower angle, and it's not as hot, right? So if I was standing here, I'd have to look off to the side or up in the sky, not directly up, but on an angle to see the sun. So the light is more spread out if we make it a different angle. So let me show you with the earth, okay? So I like to do this image, right? So the sun's light comes in parallel towards the earth. And if you look, all of these parallel lines, in this case, near the equator, or where the earth is facing the sun, we have all this light focused in one spot. But as we work towards the poles, this same amount of light is now spread out over a huge area, so it's less intense. Okay? So, let's discuss this. If I were to get sunburn, right, on a summer day, where am I going to get the sunburn? So, try that out. Where on my body would I get sunburn if I'm standing in the sun when the sun is really high in the sky? So if the sun is really high in the sky, it's coming down at an angle, right? So whatever is really facing it, like my shoulders are facing right into that, right? The top of my shoulders, the tip of my nose, maybe even the brim of my eyebrows, right? My cheeks, my bottom lip, all these things that are shown from up, right? So like if I go down like this and you're the sun, you see my shoulders, the tip of my nose, maybe my bottom lip, the bridge of my eyebrows, and these are the areas where we get sunburn because those are facing the sun, right? So just like that, the equator is facing right into the sun, right? While the poles are more at an angle, so that light gets spread out. That's the main idea behind all these things. That's why we did the flashlight lab, right? A flashlight coming in at an angle makes the light more spread, while a flashlight coming in direct or from the zenith is focused into one spot. Okay. And the more direct the light is, like near the equator, the hotter it is. Okay, I think we get the basics of that. So, the sun's path, okay? So depending on the time of the year, the sun's path changes, right? And all of this sun's path has to do with is the length of time that the sun is in the sky and the height of the sun in the sky. So, again, the sun always rises somewhere in the east, goes up to its solar noon, which is in the middle of the day, which is directly south. So solar noon is always directly south when we're in New York. And then it begins to set in the west. Rises in the east, reaches solar noon, sets in the west. Okay? So, now, the sun is going to be rising somewhere in the east, but sometimes it's south of east, sometimes it's north of east, but it's always somewhere in the east. All right? So, what I'm going to have you try to do is pick which one of these is spring. Top left, top right, bottom left, or bottom right. So, spring is actually going to be the top right. I can tell because the leaves are extra bright green. As time goes on, the sun's light actually slowly damages these leaves, turning them more of a dull green, right? And then once the temperature drops, these trees pull out the chlorophyll out of the leaves. You can check with Ms. Bouchai on this, but pulls the chlorophyll out of the leaves, and that leaves behind the actual color of the leaf, which are these browns, reds, and yellows. Okay, so what controls the path of the sun or the height of the sun in the sky? And what controls our seasons? two things. The earth orbits around the sun, or revolves around the sun. That's the first thing for us having an understanding of seasons, right? So if the earth was just still out there and stuck in this position, we would be in perpetual summer, or forever summer. Because when the axis is tilted towards the sun, here we are in New York, right? The sun's light comes in and it's north of the equator. So here's the equator right in the middle, right? So we got the poles, pole, and the equator's in the middle. The sun comes in direct north of the equator, right? If I were standing right on the Tropic of Cancer, that's what that line is. If I was standing on the Tropic of Cancer and I looked straight up on the first day of summer, I'd see the sun directly at my zenith or overhead. But lucky for us, the earth revolves around the sun. So in this setting, if I were to pick up the earth from here, it would fall towards the sun. So we would say this is the axis, or the North Pole is tilted towards the sun. Just like how over here on the opposite side, if I were to pick this up, the earth would fall away from the sun. Not that this is actually possible, but that's how I like to think of it. And the North Pole is tilted away from the sun. So in winter, the axis is tilted away. So here's a question. When the axis is tilted towards the sun, what season are we in? When the axis is tilted away from the sun, what season are we in? Now, what I like to think about is, see the axis right here? If I turn this way, now the axis is tilted towards you. You could see the North Pole. But when I turn it this way, the axis is now tilted away from you. You can't see the North Pole, right? So this is towards, this is away. So what would, boom, this be? Or what would, boom, this be? So we would call this neither tilted towards nor away. So this is going to be our equinoxes. The first day of the first day of spring and the first day of fall. So if you're looking, you're actually looking right over the equator. If you were the sun, you'd be looking right over the equator. So if I was standing on the equator, the sun would be directly overhead. And that's what's happening here and here, right? So it's not tilted towards the sun like it is here or away from the sun. It's just tilted out into space. And remember, the North Pole is facing Polaris, okay? So, main ideas, tilted towards the sun. New York is receiving a lot more direct sunlight and a longer duration, while when we're tilted away from the sun, we're receiving less direct sunlight because the sun is now overhead south of the equator, right? So that would be summer in South America and Australia, winter in North America, Europe, and Asia. And the axis is tilted at 23.5 degrees, okay? 23.5 degrees is the tilt of the axis, meaning that this shows no tilt right now because it's straight up and down. This is a 23.5 degree tilt, okay? So these are the basics of seasons. Main point, when the axis is tilted towards the sun, we receive more sunlight or more duration of sunlight and a higher angle of sunlight, kind of like when you look here, right? So in summer or June 21st, you can see the sun reaches a really, really high point and it's got a really long path through the sky, versus winter when it doesn't reach such a high point and it has a shorter path through the sky, meaning that we have less hours of daylight, right? So that's why it's so hot in the summer. The axis is tilted towards the sun. We're receiving a longer amount of sunlight and a higher angle of sunlight, most importantly. And in this winter, we are tilted away from the sun. So that means we receive a lower angle of the sun in the sky, which is, very important for it being cold, and a shorter duration of insolation or sunlight. Okay? Cool.